Great.
Good morning, everybody. Welcome to our Cybersecurity Distinguished Lecture Series. Today, we're going to have Professor Somesh Jha to talk about trustworthy machine learning. Professor Jha received his Bachelor of Technology from India Institute of Technology, New Delhi in electronic engineering. He received his Ph.D. in computer science from Carnegie Mellon University under the supervision of Turing Award winner Professor Edmund Clarke. Currently, Professor Jha is the Lubar Professor in the computer science department at the University of Wisconsin-Madison. His work focuses on analysis of security protocols, survivability analysis, intrusion detection, formal methods for security, analyzing malicious code, and recently, privacy and adversarial machine learning. Professor Jha has published several articles in highly refereed conferences and prominent journals. He has won numerous Best Paper and Distinguished Paper awards. Professor Jha also received the NSF Career Award. He is the fellow of both the ACM and IEEE. Please join me in welcoming Professor Jha.
Thank you, G.K. Ching, for having me. And a little bit trivia. Your current chair, Anish Arora, and I went to undergraduate together. So I have a deep connection with the department. It's a pleasure. G. King is for hosting me over here. And one thing I wanted to say is that, it's kind of, G. King and we were just talking, and it's hard to maintain a connection online. So I would not mind, if it is okay, if somebody has a question, just unmute yourself and ask. It keeps the flow a little bit more lively. And I think it just makes for a better just better back and forth. And G. King, if you see something on chat, just unmute, just ask me, please. Okay, so we'll start. The purpose of this talk is really not a survey. I want to get enough background in this emerging, I would say emerging field, although there are a lot of papers now in this topic, and especially sort of invite researchers in ML and security to kind of jump into this a little bit. What I find is, so one of the frustrated thing that I have, this talk comes out of some frustration. So the thing is, when you submit ML security papers to security venues, they completely miss the ML part. And then if you submit an ML plus security paper to, or even ML plus, when I say security, I mean security and privacy, by the way. So I don't want to, so I should have maybe said ML plus SNP. If I submit an ML privacy security paper to ML venue like ICML, NUDIPS, they sort of just almost not consider the security privacy part. So in some sense, one of the things that, I had a long discussion about this with one of my colleagues, Patrick McDaniel, and it seems like we need maybe a conference that sits in the middle, because it looks like, anytime sort of you kind of, I'm just sort of, you miss both. So hopefully, some of that frustration that I've had will come through. If you want, there are plenty of very good tutorials on this topic. So I know Zico Coulter and Alex Madri had last year at ICML a very nice tutorial on this whole subject. So this is not a tutorial. This is supposed to be more like a sort of a thought-provoking thing so that we can go back and forth. That's why I said unmute yourself and ask a question. Although I believe privacy and fairness are part of trustworthiness, I'm not going to focus too much on that. Okay. So key takeaways. If you already agree with this, you can mute my presentation and check your email. So this is sort of my case. What I want to take away from this is that trustworthy ML needs a system level perspective. Okay, and we need more security, privacy, crypto folks to cross over. People are already doing that, but we need more. And we need more systematic way of evaluating resilience of these, ML components. Okay, if you already believe that these things are true and you don't need to listen to the talk, okay, go ahead on mute me, go on Twitter, check your email, whatever. Okay, good. So hopefully this is my case. I can make this case better than these two people on the screen that tried to make a case that there were a lot of fraudulent ballots. I can hopefully do a better job than these two people making my case. So I don't need to say this. Believe me, like maybe a decade back, you had to make a case that ML is important. Now we don't need to do that. ML is used everywhere. Okay. Okay. Now, our story begins, if you remember 2013, there was a spate of articles coming out, even in popular press, that, hey, somehow machine learning is getting better at some tasks than humans. I don't know whether you remember, there was like a whole sorts of articles like in New York Times, I think CNN, and they had a lot of these people come on. So for example, they were better at recognizing objects and faces than actually humans, okay? They were better at solving CAPTCHAs, okay? Now, this is why I think maybe the CAPTCHAs, it looks like I had to try 2 or 3 times before I get my CAPTCHAs right these days. Maybe this is the reason, I don't know. And this is more for, there are plenty of doctors in my family who still believe that I'm not a real doctor. I'm a fake doctor. So this is more for them. In 2017, there was a spate of articles that came that actually, that a lot of medical tasks, ML sort of techniques were getting better. Sort of, for example, reading radiology readings and so on and so forth. Okay, good. Now, but I think what people did not realize, and I think it started coming out kind of maybe a couple of years after 2013, that if you deploy ML in, let's say, adversarial settings, where there is an adversary, weird things can happen. Okay. Now remember, this is a little bit before adversarial machine learning and trustworthy machine learning. This is still starting of the field, and people hadn't even coined the term, I think, adversarial machine learning. But people started noticing weird things like, hey, if I poison the data set a little bit, then I can have chatbots start tweeting some weird things. But given our last 4 years, maybe they were not that weird. And same thing, like, hey, what happens if you do ML, if you have ML components in a autonomous driving car? Like you could bypass YouTube filtering by altering videos a little bit. So people started noticing, saying, hey, yeah, ML is great. It's doing great things. But what about in these settings where there might be an adversary present? And obviously, this is from my colleague Sanjit Sesha. It is used in many safety critical systems like robotics, drone navigation, autonomous driving. And so this is not like a concern that is just out there. By the way, one thing I wanted to say is that I was reading an article a few weeks back from some IBM folks that finally they're seeing these adversarial machine learning based attacks in the wild. They're actually seeing them. So this is not just this is not just academics writing papers and trying to get tenure. This is becoming a real problem. Okay. So before we jump into my talk, I just wanted to say, and this is something that somebody once asked me from a different field. We have a very strong database group here at Madison, and also a very strong architecture group. And one of the faculty here asked me, he said, you know, what sets security, privacy, crypto people apart? Okay, what is our DNA? What is different about us than, you know, sort of a genetic systems person or a database person, architecture person, a theory person? And that got me thinking. And actually, I probably gave not a very good answer at that point, but it started thinking, and I actually did some digging into it. Some of my colleagues, I asked them, what do you think is the difference? And it's kind of what came out was this genesis. So generally, when we evaluate security, privacy, and crypto people evaluate their systems or protocols or primitives. And by the way, I'm trying to lump all of the three together here. And, you know, maybe I am probably missing some of the nuance, right? I mean, there's like crypto people have slightly different things than privacy over security, but this is kind of the gist of it, if you will. You basically have a system or a primitive sys, and then you have a security goal, and there is a threat model, basically, which is a specification of what can an attacker do, okay? And then you need a security assumption. Like in crypto, you might say, oh, factoring is hard, a shortest vector problem in a lattice is hard, or whatever. In systems, it might be, hey, there is a certain part of the TCB, like the shadow stack or the trusted execution environment, that I cannot tamper with, right? So in some sense, even if, I don't mean just crypto, even when you write systems, G-King would agree with me, whenever we write security paper, we have these components in mind, at least, even if they appear in English. By the way, one thing that I always think is, people think, when I say something rigorous, people think Greek symbols. A paper doesn't need to have Greek symbols to be rigorous. I've seen systems papers that, for example, if you look at the original paper on ROP by Hovard, there's not that much formalism in it, but it's very rigorously written. So rigor doesn't mean math symbols. Okay, so, and generally our security arguments or proofs go like, if A, following the trust model can violate the security goal, which can be like altering the control flow integrity of the program, or distinguishing between two ciphertexts, whatever, right? Then A has to violate the security assumption, okay? Which can be either you tamper with the TCB or you're able to solve some hard problem efficiently, right? So that's kind of like, the last statement is kind of saying that in a more formal way, right? So this is kind of like what we believe, even if, as I said, we don't have to do a proof. Even our papers kind of argue like this a little bit, right? I think, G-King, you remember the original control for integrity paper, even though, I mean, I wouldn't say that was, for a formal methods person, that paper was not like super formal, but essentially what they basically did is they said, oh, if you can violate the control flow integrity of the program, that means you can have a path that doesn't follow the control flow of the program. That means you must have tampered with one of the addresses they put, right? So in some sense, even though some of these arguments and proofs are going to be implicit, this kind of general kind of mindset is there, right? Now, how do systems and primitives get broken? Well, shoddy proofs and arguments, right? You know, your proof and arguments are shoddy. Your threat model is too weak. Your security assumption is not valid. I don't know how many, I don't know the average age of the audience here, but there used to be a lot of crypto systems based on NP complete problems like subset sum and so on, and those were all kind of broken because the idea there was that well, a problem being NP complete is basically a worst case argument, but the instance that you might be using in your crypto system might be easily solved, right? So in some sense, sort of a problem being NP complete doesn't say anything about average case complexity. So that's what I mean. Now, so the first three are, I would say, not super interesting. Like they still happen quite a bit, but they're not super, like they don't move the field. It's just like, for example, I won't say which one. One of my students was just looking at, actually he's one of Ninghui Lee's student. We were looking at a paper from last year's Oakland carefully because it was related to something we are doing, and the proof was incorrect. Okay, the proof was just plain wrong. It was a differential privacy paper and side channel paper. Now, to me, that is okay, sure, that is, I think, interesting, but that's not what moves the field, right? I mean, they just got it wrong, basically. Now, where it basically gets very interesting is if in security we find some really brand new vectors and attacks, okay? So if you remember, again, it's funny, like as I'm getting older, all my examples are going flat because the audience is getting younger. So that's kind of happening. Even this happens in class to me too. All my jokes are getting all flat because all my movie references are older than the students that were born. So I think if just hopefully that's not happening over here. So for example, one of the first papers that came out, Paul Kocher had a paper, very interesting paper. I think it might have been in crypto or a place where basically he said that, yeah, if you can do additional analysis, like power analysis of your algorithm, that can leak information about the secret key. So that's kind of, you can think about that as a genesis of side channels, okay? And when the AutoP gadgets came out, right? When Hovab's first paper came out, I have talked to him 10 times. The paper title is not called AutoP gadget, it's called Innocent Flesh on Bone or something. And he has explained to me like 20 times why he named that. It is based on some Bob Dylan song, but I still haven't got it. Now what AutoP gadgets did is, so remember, the history here is that people were trying to do control flow integrity and basically say that, okay, I can detect when you violate my control flow, when you violate, you don't follow the control flow. But what AutoP gadgets show is that I can mount an attack by using existing gadgets in the program. And it was a game changer because a lot of the people had just not thought about it. I personally feel that AutoP gadgets paper was kind of a game changer to me. I mean, and if Jiking, you can correct me if I'm wrong, there's a lot of follow-up work that went through on that. So to me, those are much more interesting attacks. Okay, now, one thing very important is this attack fix cycle is like, hey, somebody attacks your system, some new attack comes out like AutoP gadgets or side channel, and you fix your issues, is a very interesting part of our mindset, right? It's a security, privacy, crypto people. This is kind of our bread and butter. It's like this back and forth between people who sort of attack and people who fix. And actually, it's very interesting in security and also in crypto. Somehow the people who attack and people who fix are a little bit disjoint. There are some people who are very good at attacking, and there's some people, so it is not, there is an overlap in the community, but maybe not that much. But one big thing is, if your system protocol primitive is broken by somebody, at least I don't take it personally. I don't know, Jiking, I don't know what you feel, but I don't take it. I mean, we don't take it very personally. I mean, it is part of our ecosystem in some sense. Obviously, if it's a trivial break, then you feel bad saying, oh my God, this was a trivial break. Why didn't I see it? But at least, I don't know, I don't take it personally. What about you, Jiking?
That's a great point. So here I'm curious about attacker fix cycle. What do you see future cybersecurity will evolve? When we will terminate this cycle, attack and fix?
Well, I don't know, right? Because I think the problem is what happens is our cyber ecosystem is changing. So the threats change, how we use different things change. So I don't know whether this cycle will maybe become slower as we get better, but I don't know whether it will completely get fixed.
Well, formal methods, you're expert there. Will that help here?
Maybe it can increase the cycle, right? But I mean, I'll give you what happens in formal methods. In some sense, scale, for example, there are a lot of formal methods, and we might talk about it a little bit in verifying neural networks, verifying robustness properties of neural network. And what happens is every time there is a new algorithm, the ML field moves forward. The neural networks get bigger. So then they get out of the reach of some of them. Then the formal methods people catch up. So I think my hunch is this cycle might become longer, but it will not stop. So for example, I don't know whether you guys have, I have been reading blogs about this pipeline hack that has just come out. It's actually, from security point of view, it's not super interesting, but they were very clever in finding these systems that, control these pipelines. So it's more was about surveillance than any advance in the attack vector. Okay, so let me give you an example. I don't know how many you remember when Meltdown and Spectre came out, and the architecture community kind of reacted not very well to that, okay? Because it was attacking a huge number of years of their research on speculation. And they were like, oh, what is this attack? This is some sort of like academics just sitting there and, making some stuff up. And what is this? It is, in fact, we had some job candidates, and it was very clear that they just were not buying it. They thought this was just some sort of a curiosity that some people just wrote to get tenure. Basically, that's basically kind of the thing. But now look at that, right? Now what it is that you open up ISCA and ASCLOS, third of the papers are about this, about fixing this, that, so on and so forth. Just 1 second, Ziching. I'm going to actually turn my browser was on. I'm going to just turn that off so that there's not ting, 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 ting coming up. Ooh, 1 second. Where was I? Sorry about that.
No problem.
Okay, now can you see it? Yeah, okay. Now, a recent example of this. And I'm just trying to illustrate here the difference between the security, crypto, privacy kind of people and sort of people who are not in this field. There was a very interesting scheme that was in ICML 2020 called InstaHide. Okay, what it basically did is they had a way of encoding images, and you basically learn a model over these encoded images, and it got very good accuracy. Okay, it got very good accuracy. So think about this encoding as some randomized encoding of the images. Now, the whole idea here was, because you're randomized, you're learning over a randomized encoding, you are not leaking any private information about the training set. Okay? That's kind of, that was their premise. And there are other techniques to do this, like DPSGD, right? Differentially private SGD was designed so that the model you're learning is not leaking information about the data set, gives you these formal differentially private guarantees. But unfortunately, with DPSGD, your accuracy really drops for realistic data sets. So they said, oh, look, this new scheme doesn't have the same problem as DPSGD. By the way, DPSGD is now like used quite a bit. I mean, you know, I think it might be even supported by TensorFlow and so on and so forth, right? So their thing was, oh, the DPSGD, there's a big accuracy drop. So here is our scheme, which is based on this very clever encoding, okay? We started looking at it, and it basically, in some sense, violated those 4 principles of the security privacy mindset. They hadn't made their security assumption very, very clear. And they didn't have a formal proof that if an attacker can break their scheme, it actually violates the assumption. But again, don't get me wrong, it was an interesting scheme. Paper was exquisitely written. And I think we started looking at it more because we were interested in this than anything. But then we said, okay, you know, this is kind of the security argument doesn't seem very strong here. And we were completely able to break it. Okay. And there is a security privacy paper 2021. It is a very nice collaboration with people from Virginia, Google Brain, and Berkeley. But what I was extremely surprised, now, let me just say this. It was not, we took their challenge. They had put out a challenge and we actually broke it. So it was not even that, you know, but what I was really surprised was how it became like a very controversial thing. And, you know, there was a lot of discussion, and you can just Google Insta hide attack and see all the Twitter back and forth and blog back and forth that went on. And essentially, I was very surprised because, I mean, obviously you can see from the Insta hide author list, and these are top-notch people. I mean, this is an elite team of researchers, right? But I think that the key is, again, you know, they're not from security privacy community. So when you attack their system, they take it very personally. It's like I'm calling somebody's baby ugly, right? They're obviously going to say, oh, what the heck? Why did you call my baby ugly? And you know, and I was really surprised that it was that strong a reaction. My hunch is if they were from the security privacy community, yeah, they'll say, okay, yeah, that's interesting, let's fix it. Rather than, you know, this, yeah, I would invite you to do this Google Insta hide attack. It's actually a very interesting illustration of my point. Okay, now, in general, coming back to our theme of trustworthy machine learning, a lot of our technology life cycle, we keep saying, oh, design security from the beginning, blah, blah, blah. But nobody listens to us. King, nobody's listening. I know you say that in your class, I say that in my class, but unfortunately, nobody listens. They go plow on right ahead. So same thing, right? When the software revolution came out in the 1980s, you know, people said, oh, I can move stuff from hardware to software, I'll be more agile. But then nobody thought about security, and all the critical security bugs and all that stuff, failures came out. And then the techniques like formal methods, verification, vulnerability finding sort of catch up. So we are always in security privacy, despite preaching for, I don't know, 40 years, build security from the beginning, blah, blah, blah. Nobody listens. And it's the same thing in machine learning. Okay. Machine learning guys are plowing ahead. They are not listening to me and geeking at all. They're just going, designing nice algorithms, getting their accuracy up, publishing their ICML, NeurIPS papers. Nobody's listening. And so in some sense, we are really in phase one of in the machine learning. They're plowing right ahead without talking about security and privacy too much. Okay, so, but this is about trustworthy machine learning. Um, um, in general, I will take sort of an analogy from crypto, and I will say that there are two kinds of attacks on machine learning. One is what I call active attacks, where I tamper with the machine learning pipeline, like test time attacks, poisoning attacks, backdoor attacks, and so on, where actually I have to tamper with my machine learning pipeline. So this is what I call active attacks. Then there are honest but curious attacks. Okay, so by the way, I'm borrowing this kind of literature from crypto, wherein if you look in some of the like secure multi-party computation and other fields, they would say, oh, malicious attacker and a honest but curious attacker and so on. That's what I'm kind of doing. Is what they're not really tampering with your machine learning pipeline, but they somehow look at the output of the machine learning model and do something that you shouldn't be doing. Okay, it's like a peeping Tom through the door. Okay, like membership inference attacks, model inversion attacks, model stealing attacks. They don't really tamper with your machine learning model pipeline, but they're using the output to maybe do surprising things, if you will. Now there is something that I don't know how to put it, which I call ML for bad. We have used the phrase ML for good. This is just ML that is used for bad purposes. So I don't know. So I put a shovel there because a shovel can be used to do gardening, but also hit you on the head, right? So this is a similar thing. ML for bad. So I don't know how to call it. You must have seen these deep fakes, right? These fake videos of Obama saying crazy things, which you can then embed in the tweets and so on and so forth. And frankly speaking, so in one of my graduate classes, there was a student project that did something on deep fakes. It's very hard to tell. I could not tell that these were actually fake images generated by generative models and so on. There's also there are these things where you can generate fake good looking reviews that Amazon is not going to flag, and then you suddenly have 5-star reviews on your restaurant or whatever. You can do that with generative models as well. But this is, I don't know how to call this. It's basically ML for bad. That's how I want to sort of call it. I just wanted to go back to what how do we in security, how do attackers really exploit your system? They basically look at some assumptions, hidden or explicit, that you're making, and they violate, right? That's kind of the basic premise. Is, for example, when the first overflow attack came up, people thought, hey, nobody can overwrite the return address. No, you can do that. So that's how this whole buffer overflow stuff came out. So looking at somebody said, coming back to side channel, people thought, oh, nobody can look at power spectrum of a crypto algorithm. Well, you can, and that's what Kocher's paper did, and that can leak the key. Then the second is nobody can tamper with hardware memory, but well, that's what side channel things do. So I think a lot of the attacks come by looking at the assumptions underneath, which are hidden or explicit, and saying, no, I can violate that. And I shouldn't take credit for this. this is an insight that I actually got from one of Ian Goodfellow's talk. So what is the assumption that is violated in a lot of the trustworthy machine learning based attacks? So if you take a graduate or even an undergraduate machine learning course, you will say, okay, I sample my training data from some distribution D. My test data also comes from this distribution D. I define my risk and so on, and then off you go, right? That's kind of, if you take a sort of a standard machine learning class, that's kind of what they do. So there is an IID assumption that there is an underlying distribution from which you're sampling the training and the test data, right? And this was actually a very nice insight by Ian Goodfellow. Well, this assumption is really not true. Okay. It is actually not true even without adversaries being present. So, for example, you can have covariate shifts. Your test data might come from a very different distribution than training. And I think there are people in Vision. I don't know if there is anybody in Vision in the audience. You know, the domain adaptation techniques kind of deal with that, right? So the idea is you don't want your object detector to be trained in Berkeley, and then suddenly you come to Seattle and your car is crashing all over the place, right? So you don't want that. So there are domain adaptation techniques that deal with it. So even without any attacker, machine learning people have sort of started looking, you know, the test and training distributions can be different. In presence of adversary, it's definitely not true. An adversary is not going to respect that the test training is coming from the same distribution. The adversary really doesn't care. Let me give you an example. This stop sign is the first physical attack, and it was led by a team from Michigan. Kevin Eichhold is now at IBM Research. Basically, what they did is, so before this paper, all the attacks were all digital on sort of images, on, you know, like pixel images. They actually took a real stop sign and they put stickers on it. And the stop sign was, I think, basically, I think maybe classified as a 45 limit sign or something like that. This was in CVPR 2017. And by the way, this actual stop sign is now in the London Museum of Modern Art or something like that. They actually took this physical stop sign and it's sitting somewhere there. So think about this way. First of all, if an attacker finds that this stop sign screws up the Tesla's model, they're going to repeat it as many times until you fix the damn thing, right? So they are not being limited by repeating samples from some independent distribution. If some sample works, well, they're going to keep using that until you fix your system. Second, think about this way. If you take a random sampling of real stop signs, what is the problem? You know, will you get this? Are you getting this adversarially crafted stop sign? So the bottom line here is that in presence of adversaries, that IID assumption just miserably fails. Before I jump a little bit into my sort of the talk, one thing I might say is that adversarial learning is really not new. If you look at spam detection, there was a very early paper by Loud and Meek that you know, basically said by changing very simple filters, you can actually evade spam detectors. But with resurgence of sort of you know, these new techniques and some new theoretical techniques coming in, this is becoming important. Okay, now let's dive in. This is my cartoon of sort of a ML pipeline. You have your training data, you use your learning algorithm, and then some parameters, you learn some parameters, and then you can give it a test input saying, hey, is this a cat or a dog? And out comes the test output. Yeah, this is a cat, this is a dog. People have attacked so by the way, we are focusing more on active attacks here. So for example, people have looked at training set poisoning. Adversarial examples means giving you weird test inputs. People have also looked at parameter tampering and so on and so forth. Okay, so the bottom line here is people have looked at all possible steps here. Let's look at training time attacks. So Wisconsin, just like Columbus, gets a lot of snow. Okay. When I give this talk in some West Coast school, they basically, the question is, okay, what the heck is snow? So, people do track how many snow ice days there are as the number of years. So apparently our environmental sciences and all that thing, they track this very, very carefully. They have sensors all over the lakes, and they look at how often is the lake frozen. I got this slide from Jerry Zhu, who's one of our machine learning people here. Can anybody guess in the audience why? Why would you want to do this rather than other than feeling that, hey, Madison is a much worse town than Palo Alto? Why would you try to do this? Anybody?
Climate change, Somesh?
Yes, exactly. People are looking at, you want this line to be going kind of down if you believe in global warming. And by the way, I don't want to insult anybody's political sort of beliefs. I just put climate denier in Google, and the first image came up was Rick Perry's. That's why I put it there. So by looking at these data poisoning attacks is, let's say I hack into your computer. Let's say Anish has this data set. I hack into it. I change it a little bit so it still looks fine. But now the line goes up. That's the red line is the after poisoning, blue is after that. So this would be a classic data poisoning attack. And you can formalize this by saying that Alice has a data set S. Alice gives this data set to Bob. Bob picks a small fraction of this data set and replaces them, or you can sort of also add to it. And goal of Bob is to maximize the error of Alice, and goal of Alice is to learn from as much, look like it's learning from clean data as much as possible. Okay. Now this is only for untargeted. Now what I've done throughout the talk, and I'll make the slides available to Jing, is I've given some small kind of references if you wanted to dig deeper into that field. So for example, my colleague Ilias Diakonopoulos had a very interesting tutorial this year in ICML about how to learn basically robust learning in presence of poisoning, if you will. But I think this area, there is a very interesting paper, this was by Tudor in NIPS 18, which is less studied. So if I was a student, I would actually be more interested in this area, where you're not interested in just bringing the accuracy of the general algorithm down. Imagine you have I have a malware, I'm a nation state, and I want just to poison your algorithm enough so that my malware is classified as benign. So I'm not interested in general bringing your accuracy down. I just want the model of my choosing, the point of my choosing, to be classified incorrectly. So these are called targeted poisoning, and there's a relatively less work here. Okay, and I think it is in fact, if you look at ML in security contexts like malware and so on, I think it is more interesting to me. Okay, now this is very interesting. So this is more in the passive, honest, but curious model. So people are talking a lot about ML as a service. right? ML as a service basically says, okay, let's say Anish or Ji King has some data set. They build their nice model, put it up on the cloud, and then I can then query it and they make money. Okay. So for example, I might have some data that predicts how likely you're going to get some disease. I put it up in the cloud, you query it, you charge me per query or whatever, per 1,000 queries, and you make a lot of money. Just wanted to say one thing. I occasionally go to what I call non-academic industrial conferences like RSA, Java Expo. By the way, this is all pre-pandemic. I haven't gone to a conference in 14 months, of maybe 15 months now. I find that they have very good invited talks. So in one of those talks, Jeff Dean was the keynote speaker. And he said, at least at Google, this is the attack that they worry about the most. Okay. And because, in some sense, if this is not true, this rosy picture is not true, well, that kind of undermines a little bit of the cloud, ML as a service model, right? So here, the model theft is basically very interesting. So you have a classifier sitting in the cloud. I query the classifier Q1, these are the queries to the classifier, and learn another classifier G that is pretty close to F. Okay. Once I know G, that's kind of the proxy classifier. Well, I don't care. I would not query your, so I'm stealing the model by querying you. So in some sense, this is not an active attack. This is an honest but curious attack. I'm actually querying your model. Okay. But then learning G, sort of a proxy classifier. G King, you can correct me if I'm wrong. The first time I heard the term model stealing was in this Usenix 2016 paper by Florian Tramer et al. And we had a paper at Usenix Security 2020 that makes some connections between model extraction or stealing and active learning kind of more explicit. But just to give you an idea, in our Usenix Security paper, we took one of the complex models and we were able to steal it with the Google pricing API within $50. Our queries that we were able to sort of use, I think it was 50 or $75. And actually, I didn't know how to charge it on a grant, so I actually just paid my student by cash. So, so this is a big problem, I think. This basically undermines a lot of the ML as a service sort of a thing. Okay, I'm running short. Now, there is a lot of fake news attacks. You must have seen deep fakes and so on and so forth. These are basically abuse of generative models. Here also, the funny thing is that there are some methods that try to detect deep fakes. And they basically look at some frequency spectrum. The frequency spectrum of GANs might be different from what is in the natural images. But unfortunately, a lot of them get broken in the next conference, basically. So, for example, there was a lot of this deep fake detection stuff that Nicholas Carlini broke. Now, I'm going to go a little faster, Ji-Cheng, so please connect me. Test time attacks are basically adversarial examples that are used to fool a model. So like a panda added some noise becomes a gibbon, that stop signs becomes a sort of a yield sign, and school bus becomes an ostrich. Okay, so these are very well-crafted noise added to the images so that it gets misclassified. I'm going to skip, and by the way, there are galleries of these things. This is my favorite one, Tabby Cat becoming guacamole. And you can do adversarial examples beyond deep learning on various other models and beyond vision, like malware and so on. So I'm not going to get too much into it. I have a lot. I will make this available to Ji-Cheng. So one thing I wanted to say is right now, most of the models before, CAT becoming guacamole were all required access to the model, the white box model. So it was a white box attack. We have much better also black box attacks now, though they don't even require knowing the machine learning model. They just require black box queries. The first paper was this one in 2018, but there is a lot of other attacks now that do that. So these attacks are getting better and so on and so forth. Now, this is where I want to focus. The defenses have been very, 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 very sort of every new defense that comes out gets broken. So for example, there was a paper in ICML that won the best paper award that broke 6 out of 7 defenses that were proposed in the previous conference, okay, by Anish Athale, Carlini, and Wagner. Now, let me pose another question here for the audience. So generally what happens is the machine learning people publish defenses. Every year there are like 20, 30, I would say even more papers published in ICML, NeurIPS, and so on and so forth. Then this guy on the right, Mr. Nicholas Carlini and his team come through and break one after another, okay? And the idea is what they do is they go back to what you're doing. What they're doing is what I said before. They look at what are your assumptions in your defenses, and they really attack them. And these are now being called adaptive attacks. So in security, we don't want to do security by obscurity, right? So for example, if you're using AES, I know the AES algorithm, you can keep the key secret, but you cannot keep the algorithm secret. So if you have a defense in this space, you cannot keep the defense algorithm secret. You can maybe keep you might have some private randomness. So for example, there are these GAN-based defenses. You cannot say, or it's not okay in security to say, oh, you don't know that I'm using a GAN. I will know exactly what defense you are using, but I won't know maybe the private randomness, okay? And that's what adaptive attacks are, attacks where I know what defense you're using, but I might not know some of the parameters of the defense. And generally, a lot of these defenses fall through completely, okay? Sort of when you do this. And the question here is, can we systematize this, or do we have to wait for Nicholas Carlini and his team and others to break you? Can we systematize this? Let me sort of go to my main punchline here. Sorry, Zicheng, I had too many slides. I will sort of go to my punchline, and I will make this sort of these slides available. The question for the audience here is, given that all these ML models and all those stuff get sort of attacked, like, think about InstaHide, right? InstaHide was, very top-notch team, but, we broke it in a few months. Is that, can we ever have crypto-style guarantees in ML? So for example, when I have an encryption scheme, I will publish my proof that it is CPA secure. CPA secure is a sort of a model which it's secure under chosen plain text, which is a very powerful statement. And I say, hey, my scheme is CPA secure. I will publish my crypto paper and the proof and everything, and the experts look at it, give it a check mark. Well, then I'm done. I don't care when the encryption scheme is used in an IoT system or SSL or whatever. I don't care. I have this proof of it that it's CPA secure, and I just put it out there, and this component can be used as long, and this proof doesn't fall through. can we have a similar thing with ML? Can we give a robustness proof of ML components that is almost like CPA secure proof? And my hunch is no, I don't think so. The problem space needs to be considered, right? If I'm using ML to detect malware, if I'm using to detect threat intelligence or fraud detection or something like that, somehow I need to have the problem space in my definition of robustness. Okay? There is a lot of evidence of that. For example, if I have a vision algorithm for object detection, if I say everything is a cat, well, that is a pretty robust model, but it's useless, right? And there is some work. There was a paper in Oakland 2020 that I really like, actually. It's a very good read, not my paper, that has some evidence that when you talk about robustness of these models, you have to talk about the problem space. Now, I will not talk too much about some of the other work because I want to leave for questions. So I will kind of just leave with that I just will, sort of lead with that. There is a glaring assumption from Trustworthy ML where we kind of ignore, we talk about sometimes ML components by itself without looking at how it is deployed and the context. And I think that's a glaring omission from Trustworthy machine learning. So I wanted to say this is a very exciting area. Like if somebody wants to jump in, has questions, I will make these slides available. I unfortunately had many more slides than I could go through. And as I said, we need more systems perspective here. And we need more people with a security crypto mindset, which is already happening, to kind of jump into this field. If you look at our InstaHide paper, we have crypto people there, we have complexity theory people there, we have privacy folks, security people. We need more of that. And we need more systematic, automatic ways of evaluation of resilience of ML components. I will stop at that point, Jiqing, and I will take questions, please. And I will.
Thanks so much, Somesh. Yeah.
Any questions or comments? As I said, I wanted it to be more sort of a back and forth.
Anish, please.
Yeah, Somesh, thank you. That was a wonderful presentation. Many, many thoughts. So maybe I could get you to amplify a couple of things that you said. One was this idea that the difference between the average case and the worst case is worth leveraging or exploiting. Mm-hmm. So, often in other domains, you see that if you look at the instances of the problem which are showing up in the common case, then learning that is much easier than actually solving the general case.
Yes.
So what examples do you see examples in constructing attacks where machine learning is actually playing out in that sense, that it's easier to learn the attack because you're only dealing with a limited number of common cases?
Very, very good question. And our InstaHide attack essentially does that. So if you look at our attack, I'll send you the slides, Anish. We're going to give the talk in a few weeks. Our attack solves a tough graph matching problem, which is actually hard. But it turns out that for InstaHide encodings, we were able to solve this problem by just training a deep learning model.
Right.
So in this sense, the deep learning model, in some sense, ML was able to solve the instances of this hard problem that came through in breaking InstaHide.
Right.
And so, yes, that is a very interesting sort of problem. That is very interesting. Is that what you meant?
Exactly. I was thinking in networking, that's what we are finding with a lot of graph problems, that rather than solve the NP-hard problem, you look at the instances and extract the parameters for capturing that subset of graphs which are relevant.
Yeah,
so
exactly.
Yeah. So let me ask one more question. I'm sure a lot
Yeah.
of people have questions, so I
No,
don't
no,
want to
that's
take
fine.
too much time. You know, what you said about incorporating the problem domain as a way of making sure something can be verified. There's this recent trend to sort of think about, you know, incorporating semantics or physics
Yes.
in what you are learning. So in your mind, is there a distinction between sort of making the learning less black box by throwing in some semantics or specifications? Should I think of this as not black box, or is this just a way of making sure that essentially you're not, you know, learning that something is a cat by, you know, looking at some weird feature?
So are you talking about this the work of sort of like Guy Vanderbroek and all that, which basically takes logical constraints and tries to incorporate them in the learning? Is that what you mean?
So, Somesh, there is that work, but there's
Yeah.
also this case where, you know, when you lack data, you can throw in some sort of axioms or laws that the data must satisfy. And that comes from physics problems. So you know that this data is from this domain, so these laws must apply. So you can almost test that some data, you can compensate for the lack of data by almost testing whether your learning is following that law.
Yeah. So I have looked at the first kind of one where what you do is you have some logical constraint. So for example, I don't know, what you say, you put some constraint which says that the eyes have to be separated by some amount or something like that. I think that I have seen some of that work. So Anish, one thing that happens is where I've seen some of these fail, or I shouldn't say fail, but not scale, is that somehow they have to come up with a differentiable version of this constraint that they can just plug in. Okay. So the idea is, okay, so let me give you an example, and maybe this will make it clearer. So Zico Coulter has a very interesting sort of work where he has this scheme called SatNet. And the idea there is that a lot of these game solving, so let me go away from physics to game solving. Like, let's say I want a Sudoku solver, okay? Then what they do is a lot of these good deep learning Sudoku solvers, sort of in their problem encoding, they're encoding the rules of the game, okay, implicitly, which is, you can make an analogy to physics there. It's like the physics of Sudoku is being encoded in the deep learning model. And what happens there is, from what I can see, and again, my knowledge here is secondary of looking at some of this work. I don't work in that space, so please take that with a grain of salt. It is kind of brittle in the sense that what happens is that, okay, now you train this deep learning model that works on maybe some physics constraints, but maybe it was not complete, then it gets brittle. So what they want to do is, there's a huge push on actually learning these logical constraints by example. So if I show you a lot of Sudoku puzzles, and if I show you a lot of images with different lighting, can you learn these physical constraints? So I don't know. I don't have a very good answer. Now, one thing is, I'm not still sure that even if you were able to do these constraints, will your model get robust? Because maybe I can still get some of these adversarial examples, which will not violate the physics.
Right.
So yeah, I think, unfortunately, I'm kind of not very familiar with that space. So maybe I didn't answer your question as well as I could.
Yeah, I think this is pretty open-ended about the role of Yeah, and it leads to other questions in verification of these models, around safety, etc.
Now, I will say this. I have a DARPA GUARD grant, which is in this space. One of our PIs he works on acoustics. He's an ECE guy. Anish, you and I were both EE, but I've forgotten all of my signal processing stuff. He does more ML for, I don't know, acoustics and audio and so on. There, he did mention to me, again, I don't know that work too much, that once he incorporated some of the physics of the acoustics and the audio, he could get some robustness boost.
Right.
Which I, frankly, all I remember from my signal processing class is taking a Fourier transform. Beyond that, I know nothing now. So, so maybe that work is kind of more along the line of what you were saying.
Sure. Yeah, I hope we'll continue on this when we talk.
Yeah, definitely.
So we have two questions in the chat. Ted, you want to go ahead?
Let me stop sharing. Let me stop sharing that I can see. Go ahead.
Okay, this is Ted. So Ted Allen from Industrial and Systems. We've been having some real success along with a lot of other people on threat intelligence using open source data like Twitter and stuff.
Mm-hmm.
And it seems like that's the kind of stuff that can get poisoned, right? Because they don't have to break into my system to poison that. Have people been focusing on different issues about poisoning this kind of, threat intelligence stuff?
Yeah, there is a huge amount of now, Ted, less of it, I would say. So it's a very open area. So, I mean, this is not a dig on ML people, but ML people like clean data sets with very clean models. So some of this Twitter and ML and all that, these open data sets are very messy. So there's less of that in threat intelligence right now. People have looked at it, but not as much. So yeah, I would encourage you to really look at it. And I was just talking to Niels Provost, who's at Stripe now, and he says this is their biggest problem, is looking at trustworthy ML techniques in the concept of threat intelligence. Yeah, so it's actually sort of a very interesting space.
I mean, because we've been finding we can pretty much pick out what vulnerabilities are going to be exploited at OSU in advance, and it's very accurate. It's kind of amazing.
Did you try, one suggestion I would have is that these data poisoning attacks are pretty simple. Have you tried at least using these attacks? So what you can do is take some of these data poisoning things and maybe create fake tweets based on that and put it in your data set.
That's a good idea. I will do that.
Yeah, and it's very easy to do that. I think I would not suggest actually live tweeting them, but just put it in your data set and see what happens to your models.
All right, I promise to do that. Thank you.
Yeah.
Vedang, you have another question?
I think.
Yeah, hi.
Hi, Vedang.
So, yeah, so one question I had was, I don't, I'm not, systems or, crypto guy. So I might be wrong in my understanding about, certified trustworthy ML that you talk about towards the end. So one of the things in machine learning is that, this idea of generalization or,